Thank you for the introduction, and thanks for attending my talk. So I'm going to be talking about quantum homomorphic encryption, as you hope. In this talk, the quantum version of something that's homomorphic encryption. So in my talk, I'm going to give a brief introduction to quantum information. I'll be discussing some recent results that have with hands-on that is closely towards the goal of homomorphic encryption So the idea of homomorphic encryption has been around for several decades. It asks for the seemingly impossible task of being able to encrypt a message such that someone without the encryption key can evaluate a function on M without being able to decrypt M. And this was an open problem for decades until in 2009, Craig gave the first fully homomorphic encryption key, which allows any classical function to be evaluated in encryption. And today I'm going to talk about quantum homomorphic encryption. So we want to extend this nice functionality into the world of quantum information. So what I mean by quantum information, as lots of you probably know, until recently we had this nice theory for describing the world called classical mechanics, and we really liked this theory because it was very intuitive. But as we started studying smaller and smaller things, we realized that classical mechanics did not explain the behavior of the world at a very small scale. And so we needed this better theory of quantum mechanics. It still doesn't describe everything, but it's sort of our best theory right now. And this actually had implications for information theory. So what most of you probably think of in terms of information is sort of a classical picture of information. But there's actually a more general kind of information, which is quantum information, the state of a quantum system. So the first way that we would want to extend the idea of homomorphic encryption is we want to be able to encrypt quantum information. So this is a quantum state. We use this asymmetric bracket thing called a ket to denote that something is in a quantum state, and we usually use a Greek letter because those are more intimidating. And so we want to be able to encrypt quantum information, and people have studied this before, the idea of encrypting quantum information, and I'll talk a bit more about what quantum information is and what it means to encrypt quantum information. And then the other idea is that we want to extend to quantum circuits. So because we know now that the world doesn't work in this classical way, the way the state of a system evolves is sort of more general than what we thought before. So we have these sort of quantum operations that we can do. And this sends into the field of quantum computation, which you've probably already heard of. So just like a classical computation, a quantum computation can be written as a circuit, but we need different gates, different elementary operations that are quantum in nature, which describe this computation. And that's what a quantum circuit is. So imagine, for example, that I want to encrypt an integer and give it to somebody to homomorphically factor it for me. This would be possible already using fully homomorphic encryption. However, the circuit you would have to use would be a circuit in classical gates, and there's no polynomial-sized circuit for factoring. So this evaluation procedure would have to read this superpolynomial-sized factoring circuit, and it would necessarily take superpolynomial time. Whereas with quantum homomorphic encryption, Shor's algorithm gives a polynomial-sized quantum circuit and quantum gates for factoring. And so we would be able to in polynomial time, homomorphically factor an integer. So the idea is that we want to be able to get quantum speedups homomorphically. And extending homomorphic encryption in this way, we extend to really all circuits that we know of. So this would be now sort of the real fully homomorphic encryption until the next physical theory comes along and we find out that we can do something else crazy that we didn't think was possible. Okay, so yeah. Yeah, so that's a good point. So, okay, if we want to be able to encrypt quantum information, so if we have a quantum message, we necessarily need this ciphertext to be quantum. But it could be, I mean, it would be a very nice property of this encryption scheme if when you encrypt a classical message, you get a classical ciphertext. And in the scheme that I'm going to go into some detail about, which is, you can't do Shor's algorithm with it, but we do have this property, but we won't necessarily in general have this property. So it is true that if you want to delegate a quantum computation, that would be a very desirable property. But if you want to say, why don't we just use a classical encryption scheme? Well, we don't know how to homomorphically do quantum gates on that. So. And there would necessarily be intermediate steps of the computation, which are not classical states. So. Okay, so I'll talk about what I mean by quantum information and quantum circuits, and then I'll show you what I mean by encrypting a quantum state by introducing this nice concept of a quantum one-time pad, which is very similar to the one-time pad that you're probably familiar with. And then I'll talk about quantum homomorphic encryption. And of course, we're on California time, so please feel free to interrupt me and slow down. It's fine if I don't finish everything. So then I'm going to define exactly what I mean by quantum homomorphic encryption and how it's different from just the standard classical homomorphic encryption. I'll present some results and go into the details of one very simple scheme, which is for a class of quantum circuits called Clifford circuits. And these are kind of analogous to classical linear circuits. And then I'll talk about why it's difficult to extend this to a universal quantum gate set. Okay, so to start off, let me tell you exactly what I mean by quantum information. So first, as a sort of baseline, what is classical information? So the state of a system can be represented by, for example, an n-bit string. And you usually say that the size of the system is n if a system can be, if all of the different states can be represented by n-bit strings. So it could be that you have some physical system where it has a continuous state, and then it's represented by a real number. But let's suppose that you only have some arbitrary precision to which you can measure the state of the system. So we'll say that the state of a classical system is given by some n-bit string. And if we want to be as general as possible, of course, in the classical setting, we need to consider random variables. So the most general way of describing the state of a classical system is a probability density function. And this is a positive real value function on n-bit strings with unit L1 norm. So this is something that everyone is familiar with. Some examples of some random bits. So the state of a random bit could be a uniform random bit, which is 1/2 which is 0 with probability 1/2 and 1 with probability 1/2. We can represent this by this two-dimensional vector. Or the system could be in the state 0 with probability 1 and 1 with probability 0. We usually just call this 0, so this is kind of a deterministic state. Similarly, the state which we often call 1 has all of the probability on 1. And a quantum system is very similar to a randomized system. So the the state of a quantum system, we can describe it by a complex valued function on n-bit strings with unit L2 norm. This is what is commonly called the wave function. So let's look at some examples of the state of a qubit. So this might be, for instance, a photon or something. You might want to describe the state of a photon. Photon can be in many more states than for example, a light switch or flipped one. Okay, so it could be that all of the weight of our wave function is on 0. So this is just the sort of classical deterministic state 0. And we call this 0, but we put it in this weird bracket to remind ourselves that this is the state of the quantum system. And similarly, we can have all of the weight in 1. So far, boring. We could also have the weight uniform. So we have 1 over square root 2 on 0 and 1 over square root 2 on 1. And notice that we need the square root so that it has unit L2 norm. And I'm going to call this hat 0 because it is a Fourier transform of this vector. And this is sort of similar to a uniform random bit in some sense. So if one thing that we can do with, say we have a photon, we could measure the photon. So you know how you've probably heard that if you measure a quantum system, you destroy it. What actually happens, without being completely rigorous, is that your quantum state turns into a random variable. And so if we were to measure this, what we would get is we would get a random variable with probability 1/2, which is the norm squared of this on 0, and probability 1/2 on 1. So if we measure the state, we get a uniform random bit. So it's kind of the quantum analog of a uniform random bit. But unlike in the case of classical information, we also have this state. So this is the Fourier transform of 1. And there's just a minus sign here. This is another quantum analog of a uniform random bit. So if you measure 0 or 1, both of them give the exact same outcome. And this is where things become very different from in the classical case. Because unlike with a random variable, we have, these are orthogonal. So we actually have a second basis, right? With a random variable, there's only one basis. But with a quantum state, we have infinitely many bases that we can consider. And that's very important for quantum computation. So we have this sort of standard basis, and then we also have the Fourier basis. And then more generally, things can get more exotic. We can also have complex weights. And we commonly write this in the standard basis like this. Okay, so what can we do to a quantum state? So what kind of computations can we do? We could do classical computations because some of these states are classical. So what's the only non-trivial operation that we can do on a classical bit? We could flip the bit, so we could have a NOT gate. So quantumly, a NOT gate is denoted by x. So this just takes 0 to 1 and 1 to 0. And if we want to define the behavior of this gate on one of these states, we will just extend it by linearity. Okay, so what I mean by that is that if we have some arbitrary state and we want to apply a NOT gate, we just apply the gate linearly. Fair enough? Okay. So that's not very interesting because this is really just a classical gate that we extended by linearity, which you would also do in the case of applying an operation to a random variable. Let's look at a more quantum gate. So another gate we have is the Hadamard gate, and this just does a Fourier transform. So it takes us from the standard basis into the Fourier basis. And And again, we extend this by linearity. So generally, quantum gates are linear, and we also want them to map unit vectors to unit vectors. So they're going to be unitary operators. So what that means for when we want to look at classical gates like this is they need to be reversible. But we can generally look at arbitrary linear operators, or unitary operators, as our gates. Are there any questions so far? Okay, so one exception to this unitarity is this thing I talked about before of measurement. If you measure a state, this is a non-unitary operation. But aside from this sort of special case, all of the operations that we do and all of our gates that we're going to consider are going to be unitary operations. Okay. Let's compare classical and quantum circuits. So classically, we could take the set of addition and multiplication gates, and this forms a universal gate set for classical computation. So the addition gate gives 2 bits as input, and it outputs their sum mod 2. And similarly, the multiplication gate takes 2 bits as input and outputs their mod. So when we want to consider classical homomorphic encryption, since this is a universal gate set, it's sufficient to consider how can we homomorphically add to ciphertext, and how can we homomorphically multiply to ciphertext. And typically, addition is easy, and multiplication is hard. So in all of the fully homomorphic encryption schemes, at least that I'm aware of, to add two ciphertext, you really just add them, and that gives you an encryption of the sum of the 2 messages. But multiplication is something that's a lot more work. Okay, so just as we can write a classical computation as a circuit into a universal gate set, we can also write quantum computations as circuits. So in this circuit looks quite different from the classical circuit I had up before. So one thing that you notice is that every gate has the same number of inputs and outputs. And this is because all of these gates are unitary. So they have to take the same size input as output. So for example, we have this acts on a single qubit. So it has 1 qubit coming in and 1 qubit going out. And then we have this gate here, which acts on 2 qubits. It has 2 qubits going in and 2 qubits going out. And this gate is actually a classical gate. It's called a controlled NOT gate. And it's actually just reversible addition. So it takes as input qubits B1 and B2, and it outputs B1 and B2 plus B1. And of course, we extend by linearity to combinations of Okay, so this is just a classical reversible gate. However, these other gates are really quantum gates. We can't describe them classically. These 3 gates, the C0 gate, and the P gate, and the Hadamard gate, these generate the special class of quantum circuits called Clifford circuits. These are Clifford generators. And it's not actually so important for my talk what all of these gates do, but maybe I'll just tell you in case you're curious. A P gate is a phase gate, and it acts like this. So it's given by the unitary. Okay, so this is something that makes absolutely no sense classically, because what this looks like classically is it does nothing to 0, and it does nothing that makes any sense classically to 1. But quantumly, this is a very important gate. And then we also have this other gate T, which when we add it to the Clifford generators, it gives us a universal quantum gate set. And the T gate, again, it's not really important that you know exactly what these gates do, but the T gate it just rotates by an even smaller angle. p squared is p. That's true. You don't. Yeah. I guess it's not so easy to see, but it is true that you can. Okay, so let's compare again the classical and quantum case. So in classical circuits, we start with an addition gate, and this gate generates an important but sort of simple class of circuits, linear circuits. So if we only have an addition gate, we can generate some set of classical circuits, but it's not a very powerful set of circuits. And what I want you to think of as the quantum analog is these Clifford circuits, which are generated by the Hadamard, the P gate, and the reversible addition gate, or control NOT gate. So notice that the linear circuits are a subset of the Clifford circuits, since the classical linear circuits are generated by this reversible addition gate. So this set of circuits, it contains classical linear circuits, and it also contains some quantum circuits that cannot be described classically. But one thing that you can't do, this is also sort of a simple class of circuits, you can't do multiplication with Clifford circuits. So Clifford circuits are not universal for quantum computation. They're not even universal for classical computation. So you can only really do linear circuits and then some kind of quantum things. But you can't do multiplication with Clifford circuits. You can't generate multiplication with these three gates. Okay, so on the classical side, if we add the multiplication gate to addition, this gives us a universal gate set for classical circuits. On the quantum side, as I mentioned, we have this non-Clifford gate T. And if we add T to the set of Clifford generators, we get a universal gate set. Actually, maybe something I'll just mention, which I should have mentioned before. So classically, a universal gate set is something that really generates all classical functions. But quantumly, the set of functions that you could do to a quantum state is the set of all unitaries. And so you can't generate the set of all unitaries with a finite gate set. What we want in what we call a gate set universal for quantum computation if it generates a dense subgroup of unitary groups. Okay, so what that means is that we can get arbitrarily close to any unitary computation using some gates from, or using circuits in these four gates. Okay, and it actually, there's this really nice result which says that if we add any non-Clifford gate to the Clifford generators, this gives us a universal quantum gate set. So we consider in our work this quantum gate set, which again, we wouldn't need to include P gates and P squared P. But we also could have considered any other non-Clifford gate. And so in particular, we actually could have considered the gate set that we get by taking the Clifford generators and adding a gate called the Toffoli gate, which is a reversible multiplication gate. And so at the end of my talk, I'm going to discuss why it's difficult to implement a Toffoli gate. It's a bit easier to think about classically, to think about the Toffoli gate, since it's just a reversible multiplication gate. But in any case, you should think of whatever non-Clifford you choose as being the quantum analog of multiplication. And they're going to be very closely related. I think that if you could homomorphically evaluate any non-Clifford gate, the same techniques would probably work on others. Okay, so are there any questions? Yeah. The matrix, so it's just. Okay, so now let me talk about what I mean by encrypting quantum information. And this is also a bit of a warm-up. I'll talk about the quantum one-time pad. So this is also going to be, one of the main ingredients in the homomorphic scheme that I'm going to present later in the class. Okay, so I mentioned before this gate, which you probably know as the NOT gate, and you can get it by x, and it just maps 0 to 1 and 1 to 0. So here I've just rewritten it in circuit form. So if we have some input bit x, this gate just flips the bit. And if we take as input some n-bit string, and then we choose some random n-bit string a, and we apply x wherever a is 1, so x to the 1 is x, and we apply the identity wherever a is 0, so x to the 0 is the identity, that does nothing. This is just applying the classical one-time pad. So I've just written in a quantum way the one-time pad, which you're probably familiar with. So if we choose a uniformly at random, this is a way of encrypting a message with information theoretic security. Okay, so of course we could extend this by linearity, and this is an operation we could apply to any quantum state. So I want to show you why this is not a secure way of encrypting quantum information. So okay, so I'm going to choose a quantum state from the Fourier basis. Okay, so I'm going to choose okay, so this is going to be one of my Fourier basis states. Okay, and I'm going to encrypt this using the classical one-time pad, but extended by linearity. So I will choose a random key A. Okay, so this is the result. Everyone agree with this so far? Okay, so now I'm going to put this out into the world, and I'm going to suppose that this is an encrypted state. Now, if somebody were to apply a Hadamard gate to this and map it into the standard basis, the result would be this state. Okay, so there's some, so I will have either 0 or 1 in the standard basis, depending on the choice of m. And then I'll have this possibly a -1 in front, depending on my choice of a. But this sort of scalar in front of my state, this is not something that a measurement cares about. So if I measure the state, I'm just going to get m with probability 1. So you can see that I have not successfully hidden the quantum state, because an adversary could tell the difference between an encryption of 0 and Fourier basis of hat 0 and an encryption of hat 1. So if I had chosen a classical message, so if I just restricted myself to one of the standard basis vectors, which we should think of as classical, then applying the classical one-time pad would have encrypted it. But as long as I allow myself to choose from any quantum state, there's some information revealed about the quantum state if I encrypt it this way. That's right. That's right. So it turns out there's actually, maybe surprisingly, a very simple way of doing this, which I'm going to show now. So, so we'll denote this by just x to the vector a, meaning we apply this vector a, one-to-one pad. Okay, so another gate, a Z gate, just does basically a NOT in the Fourier basis. Okay, so what that looks like is it's just this unitary. So in the standard basis, it doesn't really, it's diagonal in the standard basis, so it just maps 0 to 0 and 1 to -1. So classically, it kind of doesn't really do anything, but it switches between the two Fourier basis vectors. So you can think of this as being like a NOT gate in the Fourier basis. Okay, and similarly, we can also apply a one-time pad in the Fourier basis by choosing some string A and applying Z wherever A is 1 and the identity wherever A is 0. And this does a NOT in Fourier basis. Okay, so if we take all of the circuits that we get that are generated just by these X and Z gates, we get something called the Pauli group. So to be completely rigorous, the Pauli group is actually the group of unitaries that are, some X to some vector A, and some Z to some vector B, and some phase of plus or minus I or plus or minus 1. But you should not care about this phase at all. That's needed to make this a group. But these sorts of scalar phases in front of an operator, they don't do anything. They have no operational meaning in terms of quantum circuits. So we can just focus on the X to the A, Z to B. So this is the Pauli group. And the quantum one-time pad is just to apply a random Pauli. So you choose two n-bit keys, A and B, and then you apply the one-time pad in the standard basis and the one-time pad in the Fourier basis. And possibly, surprisingly, this is information theoretically secure. So this completely randomizes state. So I'm not going to prove this, although it's actually not a difficult proof either. And I'll put a reference at the end. You can check it out. It is a simple proof, but it's still really not. But this is a very nice result, and it should give you some intuition how important these two bases are in quantum computing. So just hiding the information in both of these bases completely hides state. Exactly. Yep. Yeah, but it is also, it's also maybe surprising that you can have the quantum one-time pad, this information theoretically secure. Encryption has a classical key, and it's just twice as long as the UV in the classical one. So, yeah, I guess it is related. No, it's not. But it is turning your state into a completely random state, a completely mixed. So the information theoretically, the result of applying this to a single qubit is a random bit. Well, so yeah. No. It's like, yeah. I Yeah, exactly. So this is what in whatever your choice of basis, you have you're uniform between the two orthogonal states. It's even more than that. Like so I didn't really say this on my slide before. You can have not only quantum states, but you can have distributions of quantum states. You need now a matrix to describe this. And the result of applying this to a single qubit is the same is the same state as a uniform random bit. And a uniform random bit is the same state as a uniform random Fourier basis vector. Any basis, if you choose uniform randomly, it's an identity matrix, and the identity in every basis. This is called a maximally mixed state. Okay, so any questions before we move on? Okay. All right, so now I can talk about homomorphic encryption. So let me start by giving the classical definition of homomorphic encryption, and the quantum definition is very similar. So a classical homomorphic encryption scheme consists of 4 polynomial time randomized algorithms. We have a key generation procedure which outputs 3 keys. It takes in a security parameter kappa. And then we get a decryption key, an evaluation key, and an encryption key. And then an encryption procedure takes an encryption key and a message and outputs a ciphertext. An evaluation procedure takes an evaluation key and a ciphertext, as well as some function f, and f should be given as some circuit description. So for instance, if we choose our universal gate set to be addition and multiplication, then f will just be a list of addition and multiplication gates. And then the evaluation procedure outputs some other ciphertext, C prime. And then the decryption procedure takes a decryption key and a ciphertext, and it outputs some plaintext, which is hopefully good. And so in the public key setting, we imagine that Alice generates some keys, and then Bob encrypts a message using Alice's encryption key. And then Charlie evaluates some function f on Bob's message, Bob's encrypted message, using the evaluation key. And then Alice is able to decrypt using her decryption key. And then we would like such a scheme to have certain properties. So the first property is that we'd like it to be homomorphic. We say that a scheme is C homomorphic, where C is some set of classical circuits. If for every f in C, basically when Alice decrypts, she gets f of m, where f is Charlie's circuit and m is Bob's message. Basically that the homomorphic property works for every f in C. Okay, we also want some kind of security. So in CPA security, which is indistinguishability under chosen plaintext attack. And this basically means that no polynomial time adversary can distinguish an encryption of 0 from an encryption of 1. So this is a very standard definition of cryptographic security. And this is some way of saying that, the encryption of a message really does hide the message. And then there's one more property that we would like. And to demonstrate this property, let me show you how we can easily achieve security as well as the homomorphic property for all circuits in a completely trivial way. Okay, so this is called the trivial scheme. And we are going to construct this scheme from any public key encryption scheme. So a public key encryption scheme has a key generation, an encryption, and a decryption. It just doesn't have an evaluation procedure. And let's suppose this is, has indistinguishability under chosen plaintext attack security. So this is a secure public key encryption scheme. Okay, to start off, we're going to use the public key encryption scheme's key generation procedure to generate keys. Normally, we would, for a homomorphic scheme, we would also want an evaluation key. We don't need an evaluation key for the scheme I'm going to present, so you can just consider that it's here. Okay, so this is the key generation procedure for the trivial scheme. Just use the public key generation. Okay, and then the encryption procedure for the trivial scheme is just going to be the encryption procedure for our public key scheme. So we just encrypt a message using the public key scheme that we have. For instance, maybe it's Diffie. Okay, now how are we going to evaluate, since the public key encryption scheme doesn't have an evaluation procedure? We're just going to, the evaluation procedure is just going to be to take the ciphertext and the circuit and just concatenate them. And then the decryption procedure is going to be the following. We're going to use the public key decryption scheme to decrypt C and get a message M. And then we're going to apply the circuit F to get F of M. Okay, so this is as secure as whatever public key encryption scheme we started with. And it is homomorphic for all classical circuits. It's kind of surprising, actually, that it took so long for people to come up with fully homomorphic encryption. Okay, so clearly this is obviously cheating somehow. This is not what we want. We've managed to push all of the work of evaluation into decryption. This is not what we want. So we need one more property, and that property is called compactness. So compactness is the property that the complexity of decryption does not depend on the evaluated function F. So our decryption procedure shouldn't get harder as F becomes a larger circuit. That means that sort of forces us to have all the work of evaluating F in the evaluation procedure rather than in the decryption procedure. Yeah, that's another way we can. Yeah, I guess I think that's, I'm not sure if that's equivalent, but that's another way that you could define compactness, which accomplishes the same thing. They are at least spiritually equivalent. Okay, so if a homomorphic encryption scheme is homomorphic for the set of all classical circuits and in CPA secure and compact, then we say it's a fully homomorphic encryption scheme. Okay, so a quantum homomorphic encryption scheme is very similar. So now we're going to encrypt a quantum state, which will denote size of M, and now the ciphertext, the output of encryption, is necessarily going to be a quantum state. We also are going to want to evaluate a quantum circuit, and what we hope is that after decryption, what we get is the result of applying C to the message size of M. Okay, so the only real differences here are we have allowed, we now apply that this encryption into the quantum state, and now we allow a quantum circuit to be evaluated. So certainly this input is going to be generally a quantum state, this output is going to be generally a quantum state. The quantum circuit, as I showed you before, it's just going to be a list of gates from a finite gate set. So this description of this quantum circuit is just a classical deterministic string. There's nothing quantum going on there. These keys, they could be quantum. In one of our schemes, we have quantum evaluation keys because we provide some auxiliary quantum states. But in both of our schemes, the encryption and decryption keys are just classical. Maybe there'd be some reason to make them quantum, I don't know. Okay, and then the properties we want are also very similar. So we have now the Q homomorphic property where Q is a set of quantum circuits, and we want that the output on decryption for any C in Q is close to the result of applying the circuit. We usually allow some sort of exponentially small error in quantum computations since they're continuous computations. You can kind of think of this as just being like a probability, a very small probability of failure. And now we have Q in CPA security. So this is quantum indistinguishability under chosen plain text attack. It's the quantum version of indistinguishability under chosen plain text attack. And it basically looks the same. Now we have a problem of distinguishing quantum states. So we say an adversary, a polynomial times adversary can't distinguish between an encryption of any state psi from an encryption of a random bit. This has all the nice properties of classical indistinguishability under chosen plain text attack. Of course, we allow the adversary to be quantum, but you should allow your adversary to be quantum anyway. And then we also require compactness. The complexity of decryption should be independent of the evaluated. Okay, so let me talk a bit about our definition of security just very briefly. So at a high level, we want to say that a polynomial time adversary can't distinguish between an encryption of some state, some quantum state psi, and a random bit. Okay, and what this looks like, we set up a sort of game that the adversary has to play with the challenger. So the challenger's behavior is fixed, and we let the adversary do whatever they want to try to win this game. So the challenger generates keys and gives the adversary the encryption key and the evaluation key. And in this picture, I have double lines, meaning classical information, and single lines, meaning quantum information, just to kind of emphasize it's not so important. All right, then the adversary can do anything with these keys, and then must output some message. So this is their choice of psi, and they can keep some, they can keep some information which could be entangled with this. For anyone who cares, I wrote this psi because I didn't want to introduce notation, but this doesn't have to be a pure state here. It could be something that's entangled with this wire. Okay. Now, what is this? So this is the behavior of the challenger. The challenger is going to pick a random bit r, and depending on the value of r, so if r equals 0, the challenger is just going to take this wire and do nothing to it and then encrypt it. Okay, so if r equals 0, the challenger outputs an encryption of the quantum state. If r equals 1, then the challenger applies this box, which is going to just, throw away whatever information is here and replace it with a random bit, and then encrypt the random bit. So if r equals 1, the challenger outputs an encryption of a random bit. And the adversary gets whichever and must guess a bit r prime, and the adversary wins the challenge if r prime equals r. So this should look very much like, if you're familiar with the sort of indistinguishability and recursion text attack. Okay, so quantum indistinguishability and recursion plain text attack is a security property that says that there's no adversary, no polynomial time adversary. The adversary is described by whatever procedure happens here and whatever procedure happens here, that can win this game with non-negligible probability. So that means that the adversary, given either an encryption of the state they chose or an encryption of a random bit, all they can really do is guess which one they got. Yeah, sure. So this box, what this box does is it gets rid of whatever information is here and replaces it with a uniform random bit. So it's not unitary. This is basically like doing a measurement and then discarding the information and then replacing it with a random bit. And this wire just means that this box is done if r equals 1 and if r equals 0, this box is done. So r equals 0, the challenger outputs an encryption of the adversary's chosen state psi, and if r equals 1, the adversary outputs an encryption of a random bit. Sorry. But don't cryptography use these boxes? I mean, this is like a... Okay, yeah, but I will admit that's left in from a talk that I gave. So. Yeah, okay, this is the measurement. But aside from that, it should be... Anyway, so this is just about the security definition, and this has all of the nice properties of indistinguishability and recursion, which is maybe non-trivial, since sometimes things can be really weird with quantum stuff. All right, now I'll tell you some of the results that we have. So before I talk about our results, actually, let me talk about some prior results. So quantum homomorphic encryption has only been studied fairly recently. But something called delegated quantum computation has been studied fairly extensively, and our work builds a lot on the ideas from this. So in delegated quantum computation, you have a quantum computation that you want done, and you want to delegate it to someone with a quantum computer. All of these schemes actually do assume that the person who is encrypting the information and delegating the quantum computation also has some quantum power. And the reason that these are not homomorphic is because all of these require interaction throughout the computation. So this is the setting where, I want somebody to do a quantum computation for me, so I encrypt my information and I send it to them, and they're doing the computation and they keep asking me questions all the time. And they keep sending stuff back to me, and I have to do some stuff and then send it back to them. It's very interactive. And so that's quite different from the picture I had up before, where everything's just kind of moving forward. There's no interaction between evaluation and the person who is going to decrypt. Yeah. So I guess I should have said secure delegated quantum computing. You mean like where you verify it, maybe, or? I mean, if you don't care about security or verifiability, I guess you just give them the. Okay, yeah. So there's verifiability and there's. These all worry about security. I don't know if some of them also do verifiability, which is another thing. Some of them probably do verifiability today. Okay, and then just like maybe a year ago, people started considering homomorphic encryption, which you could think of as trying to remove the interaction in these things. So one result from last year is that quantum fully homomorphic encryption is not possible with information theoretic security, which is not a trivial statement. So of course, classically, it's kind of obvious that this is the case, that classical fully homomorphic encryption wouldn't be possible with information theoretic security. But quantumly, this is not always clear. So for example, we don't even know that black box obfuscation is impossible if you are able to use quantum information. There's lots more you could do with quantum information. So impossibility is also less clear. But it turns out that you can't do quantum fully homomorphic encryption with information theoretic security. So public key encryption without a computational assumption. Oh, okay, I see. So you could have quantum fully homomorphic encryption that's not public. So it's not known that symmetric key quantum fully homomorphic encryption implies public key quantum fully homomorphic encryption. So this is not like an obvious statement that follows from the impossibility of public key. And then there's also been a bit of work looking at quantum homomorphic encryption with information linkage. So this is kind of interesting, but unfortunately, it doesn't really say anything cryptographic. So if some bits of information are leaking, you have no idea which bits are leaking. It could be the most important bits in your message. So information leakage cannot give any kind of semantic security. So it couldn't give any quantum immutability and chosen plain text security. Okay, so we have the first results in where we consider semantic security or cryptographic security. Okay, so our goal is, of course, quantum fully homomorphic encryption, which would be homomorphic for all quantum circuits, compact, and CPA secure. So before I tell you about our results, let me just mention some of the obvious things that will use as sort of a baseline. What can we do trivially? So by not encrypting, we get a scheme which is homomorphic for all quantum circuits and compact, but it has no security at all. So that's something that we should try to improve. The trivial scheme that I mentioned before is homomorphic and secure, but it's not compact. The complexity of decrypting scales with the number of gates in the evaluated circuit. And then if we encrypt some in some way, like for example the quantum one I have showed, this is not homomorphic, but it is compact and it's actually information theoretic. So we want to try to get something that improves upon this. And so we have three schemes. Our first scheme, which we call CL, is homomorphic for Clifford circuits, and it's compact. So this can be seen as an analog of the classical scheme that is homomorphic for linear circuits. And it's pretty simple, and I'm going to quickly run through it. And so it's pretty simple, but it's conceptually important because our other schemes build upon it. So we're able to extend this to a scheme which is homomorphic for quantum circuits with arbitrary Cliffords, but only constant depth in the non-Clifford T gate. And this is also secure and compact. And then we can also extend the first scheme in a different way. We get a scheme which is homomorphic for all quantum circuits, but it is not compact. The complexity of decryption scales with the number of T gates, the square of the number of T gates. So in the rest of my talk, I guess I'll quickly run through the Clifford scheme. That might be all that I have time for, but it's fairly simple. The number. No, I mean the trivial scheme would necessarily have to apply every gate, unless of course the total number of gates is less than the total two gates. In that case, the trivial scheme would be better than this. Okay, that's a good point. So this is aux for auxiliary states because this scheme uses auxiliary states. So if that helps. So we provide some special quantum states that help you do T-gate. And then EPR is a kind of thing little in Rosen, which is a kind of entanglement. Because the scheme uses entanglement to delay the. I'll maybe mention that a bit later, but we should maybe move on. And I'll just mention actually that our first and third schemes are public key, but our second scheme is secret. All right, so now I can present the Clifford scheme. Let me first define the Clifford group. So I mentioned how we generate it, but what is the Clifford group actually? It is the normalizer of the Pauli group. So remember that the Pauli group is these things. So all of these circuits, it's a subset of the unitary group. And it's all of these circuits where we apply, some X gates and we apply some Z gates. Okay, so one way of saying that this is the normalizer of the Pauli group is that for every, when we conjugate a Pauli by a Clifford, we get another Pauli. So for every Clifford C and every Pauli, C times the Pauli is equal to some other Pauli times C. So if we look at that as a circuit, that means that if we apply the quantum one-time pad and then some Clifford C, that's like applying the Clifford first, and on top of that applying some different quantum one-time. So for every Clifford, there's some rule, F sub C, that tells us the relationship between A and B, A prime, B prime. So there's some function F sub C such that this is true for this relationship. And in fact, this function is always a linear function. This is, I don't think that this is obvious at all, but you can believe me that it's true. So for example, the P gate satisfies this equation for every 2 bits A and B. And so we write F sub P of AB equals A plus B. And for every Clifford, there's some rule like this. Okay, so this is now pretty much all we need for our first scheme, the Clifford scheme. So we have the quantum one-time pad. We're going to use that. We're going to use the definition of the Clifford group. And we're also going to use a classical fully homomorphic encryption scheme. And actually, it's very, for this scheme it's even obvious, we only need this scheme to be homomorphic for linear circuits. So the classical scheme doesn't need to be fully homomorphic, it only needs to be homomorphic for linear circuits. Okay, and here's how it works. So to begin with, we need to generate keys. So we're going to just call the key generation procedure of the classical homomorphic encryption scheme and output its keys. And then to encrypt a quantum state, we're going to choose random bits A and B, apply the quantum one-time pad, and then we're going to use the classical scheme to encrypt A and B and output the encryptions of A and B as well as the one-time pad in quantum state. So this is a kind of hybrid encryption scheme, and it is as secure as this classical scheme. So it relies on whatever computational assumptions this classical scheme relies on. And then to evaluate, so we're just going to apply the Clifford C that we want to evaluate. We're just going to apply it to the quantum state. And then, because of this relation here, we now have the Clifford C applied to the quantum state, but with new one-time pad keys. And the way we're going to get these new one-time pad keys is we're going to homomorphically evaluate the function that's associated with C to get encryptions of A prime and B prime from our encryptions of A and B. And then to decrypt, we're just going to decrypt the classical ciphertext to get A prime and B prime and use those to undo the quantum one-time pad, and we get the Clifford C applied to the quantum state. Okay, so is this to be clear? Are there any questions? So it's very simple. The extensions of adding T gates is much less elegant. Well, so the only quantum things are really going on here, and then I do have the same number. Okay, so like this sort of wire here, this just kind of means that it's a classical control. So like I'm, implementing this quantum circuit, and I'm like a classical part of the quantum computer. I just look at what A and B are and then decide what to apply here. And so similarly here, it's just a classical. And then these other things are all classical. Oh, that's a good question. So we don't consider hiding what circuit has been evaluated. That's another property that we could ask for. We don't consider that at all in our work, but you could also say that, you don't want whoever decrypts to know what circuit has been evaluated. But here, I guess with Clifford's actually, I think that Clifford's even. It might be trivial to figure out in some sense what Clifford is application is. That's right. Yeah, that's true. So we only need a scheme that's linearly homomorphic. So in our results, we sort of say let's have a fully homomorphic encryption scheme. In our other results, it's a bit easier if we assume that we can do multiplication. But even in our other results, we actually don't really need that property. So we could get all of our results with just a classical scheme that's homomorphic. I think that's sort of a good hint that somehow anything that goes beyond this would need to use the power of really a classical fully homomorphic. Yeah. So there's a bound on the depth of the circuit that you could possibly need to do a quicker. I think it might be looking like in the scale. I understand the circuit I can't see exactly, but there is some bound like that. It is really quite a simple. Any more questions? So I'll just mention some things that are kind of nice about this scheme, which is so this hybrid quantum classical scheme, we can reduce it to classical computational functions. Whatever computational functions you require for the classical scheme we use, those are the computational functions that we have, which is a very nice property because otherwise, if we have to use some kind of quantum computational assumption, nobody can study it. So you could imagine an arbitrary scheme for encrypting quantum information. And the ciphertexts are quantum states. And so the problem that you might have to consider as your hard problem might be a problem of taking an input that is a quantum state and deciding something from it. And these are generally not the sorts of problems that people study. So not very nice algorithms. So this is one nice feature. Another thing is that here we do get that if you have a classical message, the ciphertext will also be classical. So then you'll basically just be doing, if you have a classical message, you'll just be doing a classical one-time pattern. And this is a nice property because then if somebody just wants to delegate their quantum computation and they have no quantum computing power themselves, then it's very easy. It would be nice if we could extend do it while maintaining. Okay, so again, this is a summary. I'll just mention a little bit about our second and third scheme. So as I mentioned with the second scheme, we use auxiliary quantum states, and these help us to evaluate d-gates. So there's some kind of special quantum state that we can sort of prepare in advance, which helps you evaluate a d-gate. And I won't go into the details of this, but we have to kind of combine these states or allow the evaluator to combine the states in a weird way. So we have to provide them with many states and then we project L into the 2 to the L states. That's why we can only do constant depth. And I guess constant depth should be very small. And then for our third scheme, we use something called entanglement, which is some special quantum to delay part of the evaluation. So now I'm going to really just rush through some slides on adding reversible multiplication. I just want to kind of give an idea of why it's difficult. So a reversible multiplication gate is it's a Toffoli gate. And it's like this. So it has 3 bits as input, and it multiplies 2 of the bits and adds them into the circuit. So this is reversible because we keep inputs in multiplication. And as I mentioned before, if we want to do classical gates, consider them as quantum gates, we need to make them reversible. Now, you might have heard before some of the following, that looking at a quantum state destroys it. You can't copy a quantum state. Interaction with the environment destroys a quantum state. So these are all sort of part of the same phenomenon. And this is why it's so difficult to implement quantum computers, because even just having quantum memory is hard. So if you have, for example, a bunch of particles and they're beside each other in space, and suppose that this particle is in this state. But because it's so close to these other particles, it kind of interacts with them and you get a little bit correlated. But the problem is that, suppose these two particles get really close together and then this one sort of becomes, its state becomes dependent on this one. Well, having some of the state psi over here, we can't copy it, so we can't have copied it a little bit into this other cell. It must be that we have less of psi here. So if this particle learns a bit of psi, this particle must necessarily forget a bit of psi. And this is really the difficulty of implementing quantum memory. And it also makes it very difficult to implement quantum computations, because that means that, if we have anything that depends on our quantum state over here, then we've actually destroyed the state. So you have to really be very careful with your sort of information dependence. That makes everything very, very difficult. Okay, so here's some kind of simple thing that we could do to implement a Toffoli gate, which is going to not quite work. So let's suppose that we just have a classical state of 3 bits, and let's forget about we'll just forget about the one-time pad in the Fourier basis. We're just going to forget about that. So let's suppose that we just have a one-time pad, and then okay. So one thing that we could do is we could look at this and see if it's a 1, and if it's a 1, we could apply a NOT gate on the first bit, and that would give us the next one. We'll do the same thing here. If this is a 1, we'll apply a NOT here, and that will give us the next 2. So we can homomorphically, by doing homomorphic NOT gates conditioned on these bits, which are just sitting here on the plane, we can get to this state. Okay, and then we could apply a Toffoli homomorphically here, just a classical gate. State. And then we're going to do the same thing. We're going to look at this, and if it's a 1, apply a NOT gate here. And if this is a 1, apply a NOT gate here. And that gives us this state. And then we can kind of relabel A3 to get this state. So now we have implemented a Toffoli gate on our state. But of course, I was kind of oversimplifying a bit here. So actually, this is really bad notation, which we sometimes confuse ourselves with, because this is not really well-defined state. When we encrypt these initially, we have some randomness that we use, which depends on exactly what string we get here. And when we do some homomorphic evaluations, those also impact the state. So really, what we start with in the beginning is we have some encryption of A1, A2, and A3, which depends on some initial randomness R. And it also depends on C, which is the circuit that has been applied, the classical circuit which has been applied so far to these circuits. So this is now a proper description of this classical. Okay, so we can do the same thing again. Now this circuit remembers that these NOT gates were applied depending on these values. And then it remembers that Toffoli was applied. And now it remembers that these NOT gates were applied. And so now the problem is that this classical encryption here, it remembers x1 and x2. And because there's information about x1 and x2 over here, we have necessarily destroyed the quantum state, at least a little bit. So this is the sort of thing that would work classically. This would be no problem classically, but because quantum states are so picky about where the information is stored, we cannot have information about x1 and x2 over here, where it's not meant to be. Okay, so extending the hybrid scheme would be really nice for reasons I mentioned before, but it seems very hard. So here's some further reading. This is your course notes by a computer scientist. So if you're interested in market information and want to learn more, I recommend the second notes on the page are like the introductory course, and then the first notes on the page are a more advanced course, but it's all of the rigorous mathematics. Thank you very much. Okay, so it's a classical bit, but a uniform random quantum bit is sort of the same as a uniform random classical bit. So information theoretically, if you make a uniform random choice between any two basis states from any orthonormal basis, that's like choosing a random choice. Yeah. Oh, I see what you mean. Okay. Yeah, so sorry, I think I misunderstood your question. So yeah, so a uniform random bit is not the same as a uniform random qubit. It's the same as taking a uniform random basis state, or I guess in some sense it's the same as a uniform random qubit. But if you have a fixed qubit, that's sort of a deterministic state. So that's not the same as classical information, if that makes sense. I see. So if okay, so maybe if I understand you correctly, we had instead that the challenger chose either a uniform random bit and encrypted that and gave it to the adversary, or the challenger chose, I guess, a uniform random quantum state would also be like choosing uniform random. So these would be indistinguishable to the adversary. The important point here is that the adversary chooses a particular state psi, so it's not random because the adversary knows their choice. So probably over here, they at least remember how they chose psi. Like maybe they chose it to be, maybe the adversary chooses a random state in the standard basis, so it's either a 0 or a 1, but it's not to them random because they know which one it is and they keep track of it in this memory tree. So that makes sense. If the adversary chose a uniform random quantum state here and gave it to the challenger, and they forgot everything that they had done to choose that state, they forgot all of the randomness they had in choosing that state, they would not be able to win this challenge, certainly, no matter what the encryption scheme was. But if the adversary, maybe their adversary's procedure is I'm going to choose with probability 1/4, I'll choose a 0. With probability 1/4, I'll choose a 1. With probability 1/4, I'll choose a 0 in the Fourier basis, a hat 0. With probability 1/4, I'll choose a hat 1. But then they would remember which one they did. And so even though they chose it randomly, it wouldn't be like a random state to them because they know the state. But if they forgot that information, they could never win the challenge.